last time, this idea of atoms that are sharing electrons, so forming molecules from individual atoms to make up compounds, and how you can have multiple atoms kind of involved in that. So whenever you have atoms that are in a position where they're both trying to get to that full set of 8 dots around it, so they want to be like the atoms at the end, they want to have all 8 dots that they can get, and they want that to, that's kind of the ideal situation. So if you have 7 dots, like a fluorine or a chlorine, you're going to try to get to 8 by picking up something from somewhere else. So chlorine, if we went back to our periodic table, fluorine on the periodic table, they're over on the edge near the end side over kind of in your periodic table. They're in this corner over here. If you were to count how many columns over, they're in the 7th column. They're in the 7-dot club or in the 7-dot column there. And what they're going to do is they both want to try to get to 8 dots, like neon over here does, but they only got 7. And chlorine realizes that, well, I'm just 1 electron short of having 8. I got 7 out of 8. That's pretty good. Same for the fluorine. And what they do is they end up sharing 1 electron each. By sharing 1 electron, the fluorine borrows some of that electron from chlorine. It's like it has 8. It has 7 of its own plus 1 that's being borrowed. And the same thing happens the other way with the chlorine. It has 7 of its own plus 1 that's being borrowed. And that ends up being what we call a single bond or a bond between those atoms. So shared electrons create a bond. They create a bond or a connection between those 2 atoms that holds those 2 atoms together. And you can share a single pair of electrons, make what we call a single bond. You could actually share 4 electrons, like what we see over with these oxygens here. These oxygens are sharing 2 electrons that are orange and 2 electrons in black here. And they're actually creating 4 electrons that are shared. So there's 4 shared, plus another 4 on their own on the green electron atom. And then the one over here, 4 shared, plus 4 on their own. So they both have their 8 as well. So these atoms are also having 8 electrons each, and they're meeting that rule. These guys in chlorine here also have 8 electrons. Even these nitrogens are getting to 8, but these nitrogens are getting to 8 by having 2 electrons here, 2 electrons here, 2 electrons. So 6 electrons that they're sharing, plus 2 electrons that are each their own. 2 electrons on the black one by itself, 2 electrons on the green one by itself, and then 6 being shared. So you got kind of 2, 6 in the middle, and 2. So these are, one atom has 8, and the other atom has 8 as well. So one nitrogen has 8, 6 shared and 2 of its own. Same for the other nitrogen. And that's what's called a triple bond, because we're sharing now 3 sets of electrons, 3 pairs of electrons, 6 electrons. So you can have lots of kind of different sharings going on. You can even have some kind of more complicated molecules like this atom over here. These carbons are sharing 2, but they're also sharing 1 to the chlorines. But they're all different ways of kind of getting to that 8. You want to have 8 electrons around your atom in the end, whether or not they're electrons that are on their own, or they're electrons that are forming pairs. So you're trying to get to 8. So this carbon here's got 8. It's just got 8 from sharing with all sorts of other atoms. It's sharing with this fluorine up here. It's sharing with this chlorine down here. It's sharing with that carbon over there. And that's also giving 8 electrons around that carbon, because there's each one of these lines has 2 electrons. So we've got a total of 8 so far, just like we have 8 over here from the lines and the dots there. So these are going to form what we're calling covalent molecules or covalent bonds. And that's pretty much any time you have on our periodic table, certain atoms are going to form these more covalent bonds, and other atoms are going to form a different type of bond, which is more called an ionic bond. And that kind of varies with what atoms we're working with. Bunch of blank lines. So we did some practices where we actually drew these out. But then we also, so we kind of did some practices where we tried to figure out where everything is, right? So if you had carbons and fluorines here, you could actually figure out where those electrons are going to go. You could do the same thing for this nitrogen-hydrogen molecule here. But what these all have in common is if we were to look at our atoms, they're all kind of atoms on this section of the periodic table over here, as well as the hydrogen. They're all the atoms that we've kind of shaded in green that we've been working with so far. And those are the atoms that have a tendency to actually try to share electrons, versus the other atoms that are more purple colored here are atoms that are not likely to share. They're actually going to just give their electrons away to other atoms. And we mentioned a little bit before about this concept of ions, which are elements that basically have different numbers of protons and neutrons, protons and electrons. Normally your proton number, your atomic number, your proton number is about equal to your number of electrons. Protons have a plus charge, electrons have a negative charge. So as long as you have the same number of protons and electrons, you overall have the same charge. So like this atom here, 2 protons that are both positive, 2 electrons that are both negative. We have a +2 and a -2. Those are going to cancel out each other. +2, -2 goes to 0. So 0 charge overall. But other atoms are what we call ions. And that's where we have different numbers of protons, which are positive, and electrons, which are neutral. So we got here 11 positives, and we have 12 negatives. So 11 of the positives cancel out with 11 of the negatives. So we could kind of break this down, right? We have 11 negatives here, and then we have 1 negative left over. So 11 of those positives and 11 of those negatives cancel out, but we're still left over with 1 negative that didn't have any partners. So this atom here has an overall -1 charge. Same thing for something like here, right? 75 and 79. Well, 75 of those negatives are going to pair up with 75 of these positives, but there's still going to be 4 more positives that aren't going to be able to cancel out. So this one's got like a kind of +4. So whenever we have equal numbers of pluses and negatives, electrons and protons, we got a 0 charge. But if we ever have more positives, we're going to be positive. If we have more electrons, we're going to be a little bit more negative. And those are what we call ions. So a gold ion, in this case, has 75 and 79. And there's all sorts of other gold ions as well. There's golds with a +1. Some golds have a +2. This gold's got a +4. Maybe other golds have a -1. But ions are when you have different numbers of electrons and protons. And there's a couple ways that those can form. And one way is when we look at these dots and we're trying to get to 8, we may end up giving away some electrons or picking up some electrons to get to either 0 or 8, because wherever you are on your column, you're going to try to have 8 electrons, whether that means giving away atoms, electrons, or taking electrons. You're going to get to 8. And again, the 8 is just based on what column we're working with. So we're going to ignore most of this center mass over here, but 1, 2, and then jumping over to 3, all the way up to 8. Hydrogen and helium are special. They're on their own row, so they only go to 2, but everyone else can count to 8. And again, we're generally going to skip this area here when we're working with that. But that gives us an idea of how many electrons we're working with. And we're trying to get to 8 whenever we can, which we can get by kind of counting up to 8. But you can also get to 8 by going down to 0 too. And having 0 is just as good as having 8, because basically it puts you back 1 to the row before it. So if we're looking at electrons, some of these atoms may give away electrons or lose dots. Other atoms may gain dots to become either more positive or more negative. So for something like this sodium and this chlorine here, right, before we had shown things like 2 chlorines going along and forming a dot and sharing electrons. Like here, we'll just draw it again. So we got these 2 chlorines. They're sharing electrons between the 2 of them. And the thing about that, though, is that's 2 atoms that are those green atoms over here. Versus if you look at a sodium and a chlorine, the difference, one of the differences between those is sodium's all the way over here. Sodium's not one of the green atoms, it's one of these purple atoms, which we're going to call metal atoms, versus the greens, which are the non-metals. So we have some atoms that are non-metal. Those are all the green ones here. So those are the non-metal. And then we have all the purples that are metal. And generally, metal atoms, like these purple atoms, they don't want to form bonds that are sharing electrons with the non-metals. They're going to do a different type of bond that involves changing electrons around. Because right now, if we were to share, right, sodium here has 1 electron. It's in the 1 dot column. Chlorine's in the 7 dot column. We could form a bond like we've been doing before. But if we did that, where those are sharing electrons, and we were to count how many atoms each one of these atoms have, how many electrons these have, chlorine's got 1, 2, 3, 4, 5, 6, plus 2. So chlorine here has 8 electrons on it. So chlorine's happy. right? Chlorine's picked up the 1 electron it needed. It had 7. It wanted to get to 8, so it's sharing that electron. It's saying, okay, as far as I'm concerned, I'm good. I got 8. But the sodium, if we're to go on its side over here, only has 2. It has the 2 shared electrons, and 2 is a lot less than 8, right? It wants to have 8. It's only got 2. So while the chlorine is really happy, the sodium is not so happy. So the sodium's not so happy. The chlorine is happy. That's not the best way to do this for this particular atom. But maybe there's a different way. What we could do this is instead, the chlorine says, oh, hey, you have 1 electron. You want to have either 8 electrons, or if you have no electrons, that's kind of cool too. So having 0 electrons for an atom is just as good at having 8. So why don't I take that electron off your hands? That way I'll have 8 and you'll have none. And then you'll have 0. 0 is just as good as 8 from an electron's perspective, because it actually kind of pops you over to this way. You kind of get to go around the back. So if you get to the end of the row, you get to go up to the top, right? Because it goes from 11 to 10. So going back 1 is okay. So sodium's like, okay, I like that. I'll give you my electron. And then sodium's like, okay, I'll take your electron. Chlorine's also got 8 electrons now. It actually has the electron that the sodium used to have. And those both atoms are both really, really happy to do that. But if we do that, that's going to change the charge, right? Sodium is a 11 proton atom. So right now, sodium has 11 protons, and it had 11 electrons. But we're going to get rid of one of these electrons. So sodium now is only going to have 10 electrons. And that's okay. It just means that sodium goes from having a 0 charge to having a +1 charge. It's going to become sodium. And we're going to show that by putting that little plus sign there. It's letting us know that the number of electrons is a little bit off. If you give away an electron, you become more positive. And then the chlorine gains an electron. It went from having 17 protons, and originally it had 17 electrons, but now it's got 18, which means that this one is plus and this one's minus. So now we got a negatively charged chlorine and a positively charged sodium. So we have this atom here. Let's just clear out, make some space. So we're not going to form this thing with a line between them like we would for 2 green atoms over here that are sharing an electron. We're going to form a slightly different bond here. Oops. Put the dot over there. And we're going to have something like that. We're going to have a positive sodium and a negative chlorine. And positives and negatives are opposites. Opposites attract, right? Opposites attract. Positive sodium is attracted to chlorine with just about as much strength as one of these bonds that you would have where atoms are sharing, but instead it's what's called an ionic compound. So ionic compound is when you share, take electrons from one versus a polar molecule where you're sharing electrons. These are atoms that actually take electrons, and you go from having 1 electron to none. The other one goes from having 7 to having 8, but they're both happy. They're both happy atoms now, and they're physically connected to each other by this positive-negative attraction, the same way that a shared electron bond will also cause atoms to form a molecule. So this is a second way of forming molecules, and it's generally between the green metals, nonmetals, and the purple metals. So if you have a metal-nonmetal pair, something that's purple, something that's green, something from the left versus the right side of the periodic table, you're going to form compounds too, but they're going to be more in these metal-nonmetal pairs, these ionic type compounds. And we can get all sorts of different versions of that. So we can form all sorts of different ions. You can form oxygen ions that are negative. You can form chlorine ions or fluorine ions, sodium, magnesium. Pretty much any atom can form these ions. And it's going to do that by giving away electrons if they're over here, or by gaining electrons if it's over here. They're going to try to get to 8. So, right, so oxygen is in the 6th column right here. Oxygen would like to gain 2. It's got to become negative twice. It'll gain 1 and become negative 1. It'll gain 2 and become negative 2. Sodium, magnesium, lithium, all these ones here, they have 1 electron that they're going to give away. They're going to become positive 1. Versus this row here, the calciums, the strontiums, magnesiums, they're going to give away 1, and then they're going to give away a second one. They're going to become positive 2. So depending on what row you're in, you could have positive 1 ions, positive 2 ions, negative 1 ions, negative 2. Basically, just like how we figured out the dots before, we can figure out what the charge of these atoms is going to be when they try to form ions. These guys are going to have 0. This row here doesn't need to gain or lose, right? These already have 8. So you don't need to gain anything to get to 8. You don't need to lose anything to get to 8. So these ones don't form ions. So you're not going to see ions of this column right here. But you will see ions of fluorine. Fluorine's going to become -1. Chlorine's going to become -1. Bromine's going to become -1. So generally, we're going to see these little things. And again, we can tell that these are ions because they have that little charge after them. So an oxygen ion, -2 charge. Sodium ion, +1 charge. Let me just jump ahead a second to show that again. No, that's not what we wanted. Where'd the picture go? And that's, again, going to be atoms that are, oops, where'd the picture go? There we go. So that's going to be atoms that you can kind of guess that charge based on where they are, because those atoms in this row here have 1 dot. So they have something like this. So they only have 1 dot to get rid of to get to 8. So they're going to get rid of that dot versus something like over here where there's 7 dots, right? They only have to get 1 more dot to get to 8. So depending on where you are, you're either going to be easier to lose dots or it's going to be easier for you to gain dots. And that's why you're going to see generally the atoms on the left side becoming more positive, while the atoms on the right side become more negative. And again, the metals tend to become positive. The non-metals will tend to become more negative. And we can actually figure that out based on where they are in our periodic table. So if we had any atom from this column and we knew that it was an ion, they say, hey, you have an ion of this atom, you could say, okay, it's probably +1. If they say you have an ion of this atom over here, you know, it's probably -2. So just based on its position, we can kind of predict the charges. Other times we might not be able to predict charges. It's anywhere in the middle, probably not going to figure it out. This column here is pretty easy to figure out too. So it's basically +1, +2, +3. Other times they would have to tell you. They'd say, hey, this copper becomes +2, or this copper becomes +1. Any other time where it's not the first 3 columns or the last 3 columns over here, they'd have to tell you. But for those other 3, 6 columns there, we can actually figure it out. So that's the nice thing about that, is that you can actually figure those out. For those, it's a sort of predictable behavior. So you can kind of see an example of that here, right? So like this K ion here, we could kind of look at what column it's in. And we could say, all right, well, if we're working with this column here, we know that this is the column where things generally have a +1 charge. And this is generally the column with the +2 charge. Since K is there, then we would say, okay, well, that's the case for this. That's the ion that we're working with. That's the charge it's going to form. Just like if we were over here, we would say S is in the -1, -2 column. So you can kind of predict based on where it is what its charge is going to be for those. So that's a nice little thing about the ions there. But ions have a few other behaviors too that we see happening. Let's jump back to that. So ions are going to form these bonds. But why do some molecules share electrons, right? So something like 2 chlorines are going to share versus a chlorine and a sodium are going to take. It has to do with the electrons, right? So it has to do with how well atoms share with each other, their electrons, versus atoms give away or take electrons. Sort of has to do with how well the electrons actually are held to those atoms to begin with. Some atoms are really, really, really good at holding on to electrons, and other atoms are not so good at holding on to electrons. And these are what are called periodic trends generally. They're properties of atoms that are due to where it is on that periodic table. So when you look at the periodic table and you try to figure out where that atom is, based on where it is, you're going to have different behaviors of atoms over here versus atoms over here. And even as you either move this way or this way on a periodic table, you'll see certain behaviors start to happen. Certain atoms are better at holding on to their electrons. Certain atoms are better at giving away electrons. Some atoms get really big. Some atoms get really small. And it all has to do with kind of where it is on the periodic table, which is a property of the electrons. And the electrons cause atoms to be larger or smaller, or more easy or harder to give away electrons. And because we can predict those based on their location, that lets us figure out later, is this atom going to form a bond that's more polar, more ionic bond where it actually trades electrons? Or is it going to form a bond that's more covalent, where atoms actually share electrons with each other? So we can kind of see that. And so we'll look at a couple different properties. One of the properties we're going to look at is the size of an atom and how do atom sizes change as atoms move. And size actually goes as you go along a periodic table. The atoms get a little bit bigger as you move one way, and they get a little bit bigger as you move another way too. So as you go down a row from the top to the bottom, atoms go from kind of small to large. So if we were to look at kind of different atoms as you go from one row to the next row to the next row, you would see that these atoms are smaller, these atoms are bigger, and then these atoms are really big. And you would see the same thing if you were to look over here, a different spot on the periodic table. Basically, as you go down a column from one row to the next row to the next row, the atoms in that row are bigger than the atoms in the row before it. So generally, atoms get bigger. And that has to do with kind of there being more electrons, right? You go from an atom that has 1 electron to an atom that has 3 to an atom that has 10, right? You're adding more electrons. You're going to need more space to put those electrons in. You got to go, the first row got filled up, you got to go to the second row. The second row got filled up, you got to go to the third row. So just like we're filling up a concert room or a movie theater, right? As people start to sit in the front seats, the good seats, the other seats start getting filled up as well until the last few people, they got to go all the way back. There's no more room for anywhere else there. And that theater looks more filled because there's empty seats that you don't see, but now you can see the full seats. And we see that happening with atoms too. The larger the atom is, the more electrons it has. And generally, as you go down the periodic table, atoms get larger. So if we were to look at like a hydrogen right here, it's pretty small. But if we go to like something like lithium, it would be bigger. And then something like a sodium would be even bigger. So sodium atoms, a lot bigger than lithium and hydrogen atoms because it's further down that same column. So that's one that's kind of pretty easy to see. But also, what if you were to go from left to right? So if you were in the same row, if you went this way versus if you went this way. And what we see is as we go from left to right, we also see a change in size, but it goes the other way around. It actually, atoms get slightly smaller as you go from left. So you have one atom that's pretty big, and you see it go kind of, a little bit of an exaggeration here, but this kind of exaggerating the point. Atoms get smaller as you go from the big on the right side over here to the left side over here. And it's not a drastically big difference. This is some actual sizes of atoms. But that has to do with basically as you add more and more electrons, you get more and more negative. And the more negative you get and the more positive you get more positive, more negative. There's an attractive force between the positives and the negatives. And as you add more positives here, more negatives here, that force gets stronger. So there's more positives grabbing onto those more negatives, and they're pulling them closer together. And the more people you have to help pull, the tighter you can pull that together, and the smaller the atom gets. And it's not a huge difference, but it's enough to kind of notice as you go from left to right. So as we go this way, atoms get bigger because there's more rows. But in the same row, so if you had everyone in the row kind of grabbing onto the person next to you, you can kind of scrunch your row together. So we see a slight decrease as we go this way. So we see a big difference from small to large, and we see another kind of large to small trend going that way. So combining those together, you can kind of see that the smallest possible elements are going to be over here, and the biggest possible elements are going to be down here. So the bottom right, bottom left corner is going to be really, really, really big elements. And the top left corner is going to be the smallest ones. Because right, if you're going from small to big, and then now we're going to go from big to bigger, right? This is going to be huge, and this is going to be really tiny. So kind of going from that direction there. So the smallest elements end up being in the top right. Biggest elements end up in the bottom left. And that's all because of the electrons. As you add more and more electrons, you get kind of larger and larger elements. And these are some examples here, right? These are some actual sizes of elements. So you can see small to big as we go down. So we go this way, we get bigger. And we also get bigger as we go this way. And even as we go down this, right, 64, 99, 114, 113, small to big. Same thing for here, 97, 160, 190, small to big. So generally, these are the biggest, and these are the tiniest. So atoms are going to kind of go from really small in one corner to really big in another. And you could figure that out for any kind of pairs of atoms, all right? So if we knew 3 atoms, we'll pick 3 at random. So we'll say this atom, this atom, this atom, we'll do 4. So we got 4 atoms there. And we want to figure out, right, who's the biggest atom and who's the tiniest atom. We could actually rank these by figuring out kind of how they relate to each other. So you can kind of look, all right, for this atom here, is there anyone else in this column, or is there anyone else in this column here? So there's nothing else in this row. We don't have to worry about it. But this atom right here is in the bottom corner. That's the big atoms. The biggest atoms are there. So this one's kind of the biggest. I guess we'll put a number here. So that's the biggest one, number 1. So we'll say, so number 1's a really big atom. And then we would kind of say, all right, well, is there anyone else in this row? No. There is someone else in this column here. So this is atom number 2 right here. So this atom's a little bit bigger. This one's the biggest. This one's going to be kind of the next size up there. And then we'd say, all right, is there anything else in this row? No. But there is one in this direction over here. So we know that this is going to be bigger. And then this one's actually going to be kind of going there. So you can kind of see, right, are these going to be bigger, or are these going to be bigger than that, right? You know that as you go from this way to this way, you go from big to small. So this atom here is going to be a little bit smaller than this one over here, right? Because we know within this row, number 2 is big, and then number 3 is going to be a little bit smaller than these ones here because you're in the same row. So looking at just this set here, right, is this bigger or is this smaller? So we got kind of element number 3. And then we could also say, all right, well, these 2 elements here, how do these compare? And we know that as you go, just like here, right, this one's bigger than this one because this one's further down than this one. This one is bigger than this one because this one's further down. The further down you go, the bigger you get. So 4 and 3 we could kind of compare. So we know that 4 versus 3, right, you got 4 and 3 is bigger, just like 2 and 1. Right, so kind of 2 versus 1. We looked at this column right here. 2 is big, but 1 is bigger because 1 is further down. 4 is big, but 3 is bigger because 3 is further down. So we got kind of 2 numbers there. So we know that 3 is bigger than 4. We know that 1 is bigger than 2. So we just got to figure out, well, how does 2 compare to 3? And 2 and 3 happen to be in the same line going this way across. And we know that for things going this way, that this is the big side and this is the small side. So 2 is a little bit bigger than 3 because 2 is farther this way versus 3 is on the tiny side. So again, knowing that this is going to be the smallest side over here and this is going to be the biggest side over here, we can kind of rank these and say, all right, well, 1, 2, 3 with the tiniest one over there. So whenever you have atoms and you want to kind of figure out who's bigger or who's smaller, we can do that by just kind of looking at the periodic table and just comparing 2 that are in the same row and check, are they in the same row this way or are they in the same row this way? And as long as they're in one of the 2 rows the same, either same along their row or the same along their column, then you can compare them. So it's really hard to compare number 1 and number 3 directly, except knowing that this is a big section and this is a small section. But as long as you kind of can compare it to something else, it's pretty easy. You know that everything in this row we could compare. Everything in this row we could compare. Everything in this row here we could also compare and kind of gauge those different differences there. So whenever you want to try to figure out is one atom bigger than another, just kind of look at the periodic table, see are they in the same column or are they in the same row, knowing the left side is bigger, the right side is smaller, the top is smaller, the bottom is bigger, and we kind of make a little pair and try to figure that out. Oh, here we go. So this is just kind of a little practice here, and we got a nice little periodic table here, we cut out the middle part of that periodic table, but the trends would still work, right? If you were to look across, hydrogen is bigger than helium because hydrogen is further to the right. Hydrogen is smaller than lithium. In this case, potassium is the biggest, right? We go down this column here, just like we could go down this column here and say that, okay, carbon's small, silicon's bigger, germanium's the biggest. But then as we go this way, big, medium, big, huge, and then small, and then you can kind of work your way up. So this was just kind of giving some example atoms, and it gave a 4 choices, right? So we had the atom calcium, which was right here. Carbon is right here. What else we got? Germanium right here. And oxygen up here. So 1, 2, 3, and 4. And it was just kind of asking, which one of these do you think would be larger based on those trends that we talked about before? Again, knowing that things that are higher up are smaller than things that are down low, and that things that are on the right side here are smaller than things that are on the left side over here. So as you kind of move this way, you go big to small, so small to big, and then big to small. So kind of using both of those trends, we could see how things go bigger, how things go smaller. And then for our example right here, there were a couple different choices. So we know in general, these carbons, oxygens, this is going to be on the smaller side. So something down here is probably going to be bigger. And there were 2 choices that were on the big bottom. So we had calcium on the bottom and germanium on the bottom. These are both on the bottom. So we know these are 2 bigger atoms, but generally smaller to bigger in this regard. So potassium would be the biggest. It wasn't a choice, but calcium's there. Calcium's our kind of next highest choice. So of the different ones, this is probably our biggest atom on that page. Other atoms, if we had potassium's the biggest, we could choose that. So we could pick this calcium one instead. So let's see what everybody said. And responses. Yep, so most people went with calcium. So calcium's the biggest one. Germanium was probably the second biggest of all those. And then carbon, and then oxygen. So yep, so mostly everybody went with the right one for that. And germanium was a pretty good second choice as well. So that was an example kind of figuring that out. And those sizes are important because bigger atoms aren't as good at holding on to electrons. So if you had a really big atom, then what happens is the atoms that are really big, actually, it's really easy to take their electrons away from them. So as an atom gets bigger and bigger and bigger, the amount of energy that you have to pay an atom to take its electrons away, or the amount of force that you have to use, or the amount of suggestive power you have to use to convince an electron to take away its electrons is lower. So if you were trying to buy the electrons off of these atoms, the lower the energy, the cheaper it is. So low ionization energy atoms, they give away their electrons pretty easy. And generally, those are the big atoms, because a big atom's really large. It's trying to hold its electrons, and the electrons are far away. So it's trying to hold the electron out really far away. It can't get a good grip on it. And another atom can kind of easily pick the electron off. Versus if you're holding your electrons really close, then you got 2 arms around it. It's really easy to hang on to those, and no one's getting its electron from you. So the small atoms, they really snatch onto their electrons. They're not going to let them go very easy. And you have to really tug and pull and pay a lot of energy to take those electrons away. And we show that by saying they have a high energy, a high amount of force, a high amount of energy is needed to take those electrons off. So the farther away they are, the easier it is. The lower energy, the lower amount of work you have to do. The harder it is, the more work it takes. So generally, if we know from before, the big versus small atoms, right? So these are big atoms, really easy to take away the electrons from big atoms. So all those big atoms down here, it's easy to take away their electrons. They have what's called a low ionization energy, versus the really tiny small atoms have a hard time taking away their electrons, and they're going to have that high ionization energy. So if we kind of look at the the numbers, right, it kind of matches, and that makes sense, right? Big atoms are really easy to take away the electrons, so that energy that you have to pay is low. It's a cheap cost. It's a low cost. So low cost means that it's easy to take away those electrons. So really big electrons in the lower left corner, they're really big atoms, and they have a low ionization energy. So it's a bunch of L's to remember. A large atom, low ionization energy. And this was just kind of showing some examples, right? So 375 versus 1600. So it's about 10 times, it's 8 times harder to take away an electron from the top left than it is from the bottom right. And you can kind of see it going up. So it becomes really easy to take away electrons from that bottom left corner. So these atoms are very easy to lose electrons. So these atoms aren't going to be positive. These electrons are going to become negative because they're going to give away their electrons. They're going to get their electrons taken from them because it doesn't cost you anything to take an electron away from those atoms. So that's this idea of how easy it is to take away an electron. And it turns out for those really, really big atoms, they're going to give away their electrons, which means that these atoms here are all going to become positive because they're going to go from having one dot to having none. And then they become something that's positive. Or maybe they have 2 dots, right? They have 2 dots. They're going to lose both those dots and become positive. So all those metal ions, all those metal atoms, they're becoming positive because they're generally larger than the atoms over here. And that means it's easier for them to take away or lose their electrons and become positive. So that's why we see all the atoms on this side of the table being positive. We see lots of positive atoms on this side over here because these are all the atoms that are generally bigger than the atoms over there. And they're the atoms, because they're bigger, it's really easy to take away their electrons than the atoms on the other side. So it's easy to take away an electron from the side over here and become positive. And then kind of the opposite happens with the other electrons, right? So these atoms, they don't want to give away electrons, right? They're not going to become positive. They're going to stay not positive. And actually, these electrons over here, things like fluorine, chlorine, oxygen, right? Remember, they have 7 dots or 6 dots. So they don't want to give away, right? So oxygen's got 6 dots on it. It wants to get to 8, so it needs 2 more dots to get to 8. So ideally, oxygen's going to try to find 2 more dots and become negative. Just like sodium is going to give away 1 dot, or lithium, these guys are all going to give away 1 dot. These atoms over here are going to try to pick up a dot or pick up 2 dots, which means that they're going to go from neutral to negative while these ones become positive. So it's really easy to get rid of electrons here. That's why that ionization energy is low. And then these other atoms are really hard to get electrons, or hard to take electrons. The cost to take away an electron is high. And actually, the ability to give an electron to those atoms is also really high. So it's really easy to give an electron to fluorine and become -1. Versus it's really hard to give an electron to cesium and become negative, because then it would be -1 here. So these atoms here, they don't want to give away electrons, right? These atoms want to give away their electrons. They don't want to get more electrons, right? So lithium here has 1 dot, right? Lithium here has 1 dot. If we were to give lithium a 2nd dot, it would not be very happy at all. It doesn't like having 1 electron, and it really, really, really doesn't like having 2. It wants to get rid of its dots. Just like oxygen has 6 dots, and it doesn't want to get rid of 1 dot. It wants to gain 2 more because it wants to get to 8. So oxygen doesn't want to give away electrons. It has a really high ionization energy. If you try to take away an electron from oxygen, it says, no, why don't you give me an electron instead? Lithium, if you try to give away an electron, take an electron, it says, here, have 1, have 2. If you try to give a 1 to a lithium, it's like, no, 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 I got enough. I'm plenty full. I don't need any more electrons. And that's kind of reflected by this, what's called electronegativity, how much an atom wants to gain an electron. And fluorine, 4 out of 4 stars. It would take an electron any day of the week. Lithium, all these ones on the right side here, 1 out of 4 stars, they really don't want to gain another electron unless you really, really, really force them. So these ones are giving away electrons left and right, and they're not going to take any. These ones here are taking as many as they can until they get to 8. And if you try to grab one from them, they say, no, kid, go get your own. These are mine. So these electrons are a little bit greedy. They want to gain more electrons. And these atoms here are a little bit generous. They're giving away electrons. So they get along really well with each other. So if you put a lithium and a chlorine together, right, lithium says, hey, I got all these electrons. Can anybody help? Does anybody want to take an electron? And the chlorines go, oh, hey, over here, I'll eat that. I'll take that electron. So when you have really low electronegative, really low ionization energy atoms paired up with a high electronegativity, high ionization atom, it's great. These atoms don't like electrons and they want to get rid of them. These electrons are looking for anybody to steal / borrow / take from. And when they see something like this, they go, perfect, I'll take that electron, I'll become negative, you'll become positive, we'll all have 8, we'll all be happy, we'll all be good. And that's why we see the atoms on the left side of the periodic table, the metal side, pairing up with the atoms on the right, the non-metal side. And they form these ionic compounds because the metals become positive when they give away their electrons, and the non-metals become negative because the metals are big atoms and they're large atoms and they have a low electronegativity and they have a low ionization energy, which means they're really well designed to give away those electrons. And then the other atoms on the right, so these are what we call the metals. And again, on our periodic table, the metals are on the left side. So these are the metals over here, and then the non-metals on the right side here. So non-metals are generally small atoms. They're on the right side. They've got small atoms. They have a high electronegativity. They have a high ionization energy. They're tiny. So think about something really small hanging onto its electrons. It can kind of wrap its arms around them. It can really grab on really tightly. And if you try to take an electron from it, it's not going to go so well. Versus these ones over here, they're carrying the electrons really far away. They don't have too many, and it's easy for anybody to go by and grab one right off of it. So these atoms, they don't want more electrons. You try to give another electron, it's like, no, I'm full. I don't need any more. Here, take one if you can. Versus this one's going, grabbing them all it can, hold them on really tightly. It's not going anywhere. So they work out really well together when you can pair them up. So if you pair up two, a metal and a non-metal, you'll form a bond. But you could also form bonds between 2 of these. So 2 of these can come together to form a bond, or 1 of each can come together to form a bond. But 2 of these don't work so well. So 2 metals can't bond the way that 2 non-metals can, or the way that a metal-non-metal pair can. So there's combinations that work and combinations that don't. But it has to do all with the electrons and how well they hang on to each other and how well they can hold each other. And again, the large atoms, again, in the bottom left corner, so if we were to look at our periodic table, right, bottom left corner, really large atoms, really low electronegativity. It makes an L, it kind of fits in your hand. These are all the atoms that are going to lose their electrons. And then the opposite is the other corner. So the top right corner, they gain electrons. And then depending on how you pair them, you can form either ionic compounds or molecular compounds. So molecular compounds, 2 nonmetals. 2 of the things from up here, chlorine and chlorine, chlorine, fluorine. And this is where we're going to do all the Lewis dot structures. So this is where we do those Lewis dots. Structures, you know, things like this with the little dots. So whenever you see those dots and you see the lines, that's a sign that we're going to form molecular compounds. Versus over here, we're going to be doing things like pluses and minuses. So if you see positives and negatives, then you know you have an ionic compound. If you see lines, then you know you have a molecular compound. So even by just looking at the structures, if you see lines between compounds, that's an indication you have a molecule. That's one way to tell. If you see 2 atoms that are both nonmetals, they're both on the top right side of the periodic table, that's also a sign you have a molecular compound. So a couple of different ways of telling. If you have a triple bond or a double bond, that's also a surefire sign that you have a molecular compound. So a couple of different ways you can identify molecular compounds just from looking at it without having to know too much about the atoms. Is it two nonmetals? Is there a triple or a double bond? Is there dots being drawn on there? Those are all good ways of knowing. Versus the ionic compounds, if you see pluses and minuses, that's a sign that you have an ionic compound. If you see a metal and non-metal, a bottom left and a top right pair, or a left-right pair on the periodic table, that's also a sign that you have ionic compounds there. And in ionic compounds, the electrons aren't being shared. The chlorine's actually taking away the one electron the sodium had. The chlorine actually took that electron, and it went from being neutral to being negative. And when the sodium lost that electron, it became positive. So these atoms actually give each other their electrons. One atom takes and one atom gives. Versus over here, those two atoms are sharing the electrons. These dots and these lines right here means that the sodium, this nitrogen here is sharing with this nitrogen here. They're not giving or taking. They're both still holding on to those electrons, and they're both hanging on really tightly. And those atoms are therefore sharing, versus over here, this atom actually took the electrons from the other way around. So you can have compounds that share electrons or compounds that don't share, that take. So, so you have taken electrons versus shared electrons there. So that's kind of the difference between an ionic bond where you take and a covalent bond where you share. And those are kind of the two main types of bonds. And again, it has to do with what kind of molecules you have. Metal, non-metal versus two non-metals. And you won't ever see, right, there's one other combination that could exist. You could have a metal plus another metal, but we don't really see that. We don't see bonds between two metals. So you can have metal with non-metal or non-metal with another non-metal, but you don't see a metal-metal combination. So that's kind of the other option, that's a bit the other permeation that's there, but we don't ever see that one. So those are kind of different types of bonds. And again, it's basically something, if you have an ionic compound, a left-right pair, so something in blue, something in yellow on this chart here. Again, metals are on the left-hand side. The left-hand side is a lower ionization energy. It's a lower electronegativity. That means that they want to get rid of their electrons. And they're generally bigger atoms. They're larger atoms. So these are all words that start with L. And that's reminding you that the large atoms are going to give away their electrons versus the non-metal side over here are generally smaller atoms. So they're going to have high electronegativities, high ionizations. They're going to want to take electrons from other things, and they're not going to want to give those electrons away again. So they're either going to form bonds with themselves, in which case they share, or they're going to take an electron away from somebody in blue over here, in which case they form an ionic bond. So that's why these can always bond, either with themselves or with something else, versus these ones can only pair up over here because they're not going to give away, they're only going to give away electrons. They're not going to share electrons. They're going to just give them away. So if they're with themselves, they're not going to give an electron to another atom of the blue. They can only give those electrons to the yellow. So that's why we see yellow-blue pairs and yellow-yellow pairs, but not the blue-blue pairs coming together, because the blues wouldn't have anything to give their electrons to. Metals can only give electrons away to things that'll take them, and none of the metals are going to take an electron from another atom, or none of the metal atoms are going to accept an electron from another metal, but they'll give it away to the non-metals there. And if a non-metal can't take an electron from a metal, it'll end up sharing as the next best thing for those, and that's where you get the double, single, triple bonds when they start sharing those electrons instead. So that's how we can end up having shared electrons, having that molecular compound between two nonmetals. And like we had said, right, you can kind of, when you're trying to figure out is something going to be ionic versus molecular, look at the side, look at the atoms involved. Look, is it a left atom and a right atom, two right atoms, or a left-right pair? And if it is a left-right pair, you can actually figure out the charges of the atom by looking at the column, because you know these atoms all have one dot that they're going to end up losing and become +1. These atoms here have two dots. They're going to lose those two dots and become +2. So we can actually figure out for ions what the charge is going to be by where they are. We can see the sodium becoming positive, the chlorine becoming negative, all based on kind of where it is, right? Sodium can either gain 7 electrons, that'd be really hard to do, but it could just get rid of 1. And getting rid of 1 is a lot easier than finding 7, versus the fluorine, finding 1 is a lot easier than losing 7. So they're going to do the easiest path to get to 8/0, whether that means just picking up 1 more or tossing 1 away or 2 away. They're going to try to get there. And sometimes you'll see words describing these. A lot of times we just call them ions that are atoms with a charge, but sometimes they'll call them, you'll see the term cation and anion. These are, again, all ions. Ions just are atoms that have a charge that have different numbers of protons and electrons, but sometimes they'll call the positive ions. So rather than saying it's a positive ion, they'll call it a cation. And rather than calling it a negative ion, they'll call it an anion, especially if you're looking at like batteries and things like that. You'll see these terms. But if you ever see them, the easiest way to remember the difference is, again, usually they're just called positive ions and negative ions. But if you do see it, remember cats have paws, the feet of a cat or a paw, and a cat has a paw, and we could call that a positive thing or a cation. So if you ever do see cations versus anions and you can't remember which one's which, remember that cats have paws, so cations are the positive one. But generally they call them positive ions and negative ions, but if you ever see that there. So for our cations here, right, the metals generally are going to form cations or positive ions. And we can tell by just the dot structures of something, generally how many ions it's going to have, right? If you have 1 electron and you want to get rid of all your electrons to get to 0, well, you only have to get rid of 1 to get to 0. So you're going to get rid of 1 and become positive 1. If you have 2 electrons and you want to get to 0 electrons, you get rid of 1, you still have 1, so you get rid of the second one too. So you become positive 2. And you see that all the atoms in that first column generally form cations, positive ions, with a +1 charge. All the atoms in the second column form positive 2 ions or positive 2 cations, and so on. And then generally the other one that's predictable is this third row here for 3. And then on the other side, something like chlorine has 7, and it wants to have 1 more. It wants to get to 8. So it can get to 8 by sharing, or it could take an electron from one of these over here. And if it takes an electron, it's supposed to have 7. It now has 8. So it ends up with a -1 charge. Same thing for something like this over here. Would normally have 1, 2, 3, 4, 5 dots. But it's going to go and pick up 3 more dots from other atoms. And when it does that, it gains a -3. So this column here, -3 ions or anions. This column here, -2 ions, -1. And again, this last column on the left, these already have 8 dots. This one here has 8 dots already. So it doesn't need to pick up any dots from anybody. It already has 8. This one doesn't want to give away any dots because it already has 8. It's not going to do that either. So these ones don't get a charge. They don't become positive. They don't become negative. They say, I'm perfectly fine the way I am. I don't need to pick up any more electrons. I don't want 9. I want to stay at 8. I don't want 7. I want to stay at 8. So they're not going to gain or lose electrons. So that's why we said that one, even though it has 8 dots, it's got a 0 charge. So generally, atoms can go from 0 to 1, 0 to 2, 0 to 3, or 0 to -1, -2, or even -3. And if you wanted to guess, if somebody said, all right, guess anywhere on this periodic table, what atom would have a -3 charge? Your best guesses are the ones in this column here. Just like the best likely ones to have a +1 charge are the ones in this column here. So we can kind of guess just based on the periodic table what atoms there are. And sometimes we can't. You can't tell. We'd have to tell you. For anybody else that's not in the first 3 or the last 4 there, we'd have to tell you. But for some of them, there's a good guess for those. So just like with this potassium, right? Potassium K in the first row here, generally going to form +1s. So we had just kind of one more little practice one of these. So same thing, this was asking for O ions. So ions of oxygen would be, oxygen would get a charge on it. It may become positive, it may become negative. And you can guess, right? It's not in the first column right here. We know these guys are the +1 electrons. Same thing for +2, +3. So you can kind of try to find oxygen. Oxygen's O. And you can see based on where that is it more likely to be +1, +2? We had choices, right? So we had choices. So these are all different ways of writing oxygen. These are all oxygen ions. This is oxygen that's picked up 2 electrons and become -2. Oxygen that picked up 1 electron became a -1. Oxygen that actually isn't an ion, that's just oxygen, it's neutral at 0. And then you could even go up to +1 or +2. Oxygen could give away 15. Oxygen could give away 1 electron and become +1. Oxygen could give away 2 electrons and become +2. So these all exist as options, but some of them are more likely to happen than others. And one of these is very likely to occur, and that's kind of based on, we'll do this one more time, based on where it is. So based on where this atom is, hands in the wrong spot, oxygen's right here, right? So oxygen's here. So based on that column, you can predict a certain behavior. The fact that oxygen is a non-metal versus a metal means it's likely to exhibit a certain type of behavior with its electrons, right? Is oxygen a big atom or is oxygen a small atom? Oxygen being a non-metal is a pretty small atom. Oxygen is on the upper right side, so it's not a large atom. It's not a low ionization energy atom. It's not a low electronegativity atom. It's an electron, an atom that likes to have electrons, and it wants to have as many electrons as it can. So it's going to try to snatch as many electrons as it can from other atoms. So based on that, we could rule out these positives and these zeros. So it's either A or B. And then what we would do is we would look and say, all right, well, this is the 0 charge column, the -1. Oxygen's in the -2 column. It's got 1, 2, 3, 4, 5. Oxygen has 6 dots. It would love to get to 8. Well, if it picks up 2 electrons, it has 8 dots. And that probably means that A is the answer. And everyone went with that, right? Everyone went with the right choice, the -2 choice. So good. So that was that. I think we'll skip that one. So we'll skip that one and look at that another time. So those are our kind of ways of looking at charges. So we'll kind of wrap that up here, but we'll just kind of introduce this idea for next time that when you have atoms coming together, right? So something like this sodium and this fluorine, sodium's going to give its electron to the fluorine. Sodium's going to go from +1, 1 dot to +1. Fluorine's going to basically grab that dot. And then one has a -1 charge, one has a +1 charge. And again, opposites attract. The positive sodium now is attracted to that negative fluorine that just stole its electron away. And we form this molecule here, NAF. This is an ionic compound. And you'll see all sorts of different ionic compounds getting formed. Sometimes it's +2 and -2, +1 and -1, depending on what you get. But if you do have mixed charges, right, +2, -2, those come together no problem. This one's -2, this one's +2. They end up canceling each other out. The plus and the -2 go away. But what about here where we have a +1 and a -2? Those could also attract each other, but overall there would be Na and +1 and O -2. The oxygen wants 2 electrons and the sodium only has 1 to give away, right? Sodium Na+ has 1 electron. Oxygen wants 2 electrons if it can get it. So to get 2 electrons from sodium, the oxygen's going to need 2 sodiums to form that bond. 1 sodium gives 1 electron, the other sodium gives the other electron. The oxygen's happy now with 2. So when we form this ionic compound, we end up with 2 sodiums and 1 oxygen together. So there's 2 +1s and 1 -2. Those numbers equal each other in the end. 2 times 1 plus 1 times 2 equals 2. And you can get all sorts of different combinations like that, just like this here, right? Ca2+, 2 pluses. I'm going to need 2 minuses to cancel that out. So not 1 Cl, but 2 Cls. So we can form these ionic compounds where the charges cancel out. Or I could just take an Na and a Cl. 1 is plus, 1 is minus. Those cancel out. So whenever you're making these ionic compounds and you're checking you have something on the metal side and something on the non-metal side, part of the reason we need to know the charges is to figure out, do the charges cancel each other out? And in this case, they do, because I got plus 2 here, and a 2 times minus 1 over here. Here, plus 1, minus 1, those cancel. Same on the previous page. So double check that your charges all cancel, that your minuses and your pluses come together in the right way. And as long as they do, then you'll form the right kind of pairs with those. So those are just some examples of ionic compounds. Oops. Skip that. So we'll work on that again next time. But that's probably a good spot to stop overall for those. But this is, again, looking at how molecules come together and form all these different kind of compounds, how they form these different structures that have positive and negative charges, whether or not that's sharing electrons or borrowing electrons or taking electrons. Some are ionic compounds, some are molecular compounds, depending on kind of those pairs. And we can figure that all out based on where they are, and we can use these little dot structures to kind of figure that out too. So kind of between where they are, what spot they're in, and how many dots they have, we can kind of model behavior of certain different types of atoms. So that was a good spot to stop. Any questions about any of these?